Okay. Okay, folks, so this is lesson 2 on complex numbers. I'm going to introduce you to something called de Moivre's theorem. De Moivre's theorem is a quick, easy, efficient way to find a power of a complex number, although we shall see that we can use this at some point to actually prove trig identities. Just to try to explain it to you, let's imagine we have a complex number which is written in polar form. R cos theta plus I sine theta. So R denotes the modulus of the complex number, theta denotes the argument of the complex number. Then let's see what happens if we square it. Well, Z squared means you do R brackets cos theta plus I sine theta squared, which means you times it by itself. And if you do that, you will get R squared into, because you times the moduluses together, R times R is R squared. And then you add the arguments, theta plus theta is 2 theta. So you get R squared bracket cos 2 theta plus I sine 2 theta. Okay. Now, if I was to do this again, I would get Z cubed is R cubed into cos 3 theta plus I sine 3 theta. If I was to do it to the power 4, I would get R to the 4 into cos 4 theta plus I sine theta. So de Moivre's theorem states the following. If you do R brackets cos theta plus I sine theta, all to the power of n, you just do the power of the modulus r to the n, and you multiply the argument by theta, cos n theta plus I sine n theta. Now, 3 key things. One is this is on the formula sheet. It is stated on the formula sheet. Second is, if you follow what I did earlier, you will definitely believe that this is true if n is a positive integer. N is 1, n is 2, n is 3. But this is true for any integer which can be a positive or a negative. What am I doing here? What am I doing here? Which can be a positive or a negative integer. So this is true for positive and negative integers. It works when n is -6. It works when n is 10. It kind of works when n, the power is a fraction. We will come back and do some more work on fractional powers, by which we mean square roots, cube roots, etc. at a later stage. And the other thing to say is, when you write this in exponential form, it just looks obvious. In exponential form, this says if you expand r e to the I theta to the n, you just do r to the n e to the I n theta. And that just looks like you're multiplying out brackets. R to the n times e to the I theta to the n times the powers together, and we go. So it looks completely obvious. Now, this can be proved. You can prove it by induction. Again, there's a proof in the textbook if you're interested. I'm not going to do that. If you want to look at the textbook, please do so. I'm just going to go through a couple of examples using that. So this question says, use de Moivre's theorem to find a 1 plus I to the power of 11. We'll worry about b in just a minute. So in order to do that, I am first of all going to have to write 1 plus I in either modulus argument form or exponential form. Now, the easiest way to do that is type in 1 plus I and then convert it. So just remember what you do, folks. 1 plus I. If you press Option, Calc. No. If you press Option, F3 complex, F6, F3, you'll get its modulus is √2 and its argument is 1/4 pi. So this is the same as √2 into cos 1/4 pi plus I sine a quarter pi. So consequently, 1 plus I to the 11 is the same as root 2 into cos a quarter pi plus I sine a quarter pi to the power of 11. Now this is de Moivre's theorem, so that's the same as root 2 to the 11 times cos of, if you times the argument by 11, you'll get 11 pi over 4 plus I sine 11 pi over 4. That's de Moivre's theorem. And then to convert that back, probably the quickest way is to do, so this is the complex number whose modulus is root 2 to the 11. Root 2 to the 11. Angle, which is that? And the argument is 11 pi over 4. And that gives you that, minus 32 plus 32i. Now, I think actually that modern calculators will do this without Moivre's theorem. So as a check, if you type in 1 plus I to the power of 11, you do indeed get the same thing. B, once we simplify 1 over 1 plus I to the power of 5. Now, because de Moivre's theorem works for negative powers, what I can do is write this as 1 plus I to the minus 5, which is therefore, using what we did earlier, root 2 brackets cos a quarter pi plus I sine a quarter pi, all to the power of minus 5. So that's the same as root 2 to the minus 5 times cos of minus 5 over 4 pi plus I sine of minus 5 over 4 pi. Raise the modulus to the power n, multiply the argument by n to give that. And then again, converting that back, we're going to get the following. So this is the complex number whose modulus is root 2 to the power of minus 5 and whose argument is minus 5 over 4. Whoops, what happened there? 5 over 4 pi. And that will give you that. So minus 1/8 plus 1/8 pi. I'm pretty sure your calculator will do that as well. 1 over 1 plus I to the power of 5. Second one, folks, I want to simplify this expression. Cos of 9 pi over 17 plus I sine 9 pi over 17 all to the power 5 divided by sine cos of 2 pi over 17 plus I sine of 2 pi over 17 cubed. Now, I want to do that. I would like to simplify the top and bottom using de Moivre's theorem. There is no number in front. There is no argument. There is no modulus. The modulus is 1. So you have to worry about that. And then we'll worry about dividing them afterwards. Now, the top is easy. The top I can write as cos of, multiply the argument by 5, so you will get 45 pi over 17 plus I sine of 45 pi over 17. The bottom, we have a problem because there's the wrong sign in the middle. It has to be a plus in the middle of an expression of the form cos theta plus I sine theta. But that's okay because I can write the bottom as cos of minus 2 pi over 17 plus I sine of minus 2 pi over 17. Because the cos of a negative is the same as the cos of a positive, the sine of a negative is the same as the negative of the sine. So on the bottom, that will give me cos of minus 6 pi over 17 plus I sine of minus 6 pi over 17. So that's what we get if we divide them. Then these are two complex numbers whose moduluses we know. When we divide them, we subtract the moduluses. So that will give me cos of 45 pi over 17 take away minus 6 pi over 17. We'll take away a negative is adding. So that's 51 pi over 17 plus I sine of 51 pi over 17. Well, that's just cos 3 pi plus I sine 3 pi. If you think about it, 3 pi, what is that? So that's pi, that's 2 pi, that's 3 pi. So this is a complex number whose modulus is 1 and whose argument is pi, because 3 pi is the same thing. That's minus I. That's where we're at. So that's going to equal minus I. But again, your calculator will happily deal with this. This is a complex number whose modulus is 1 and whose argument is 3 pi. And it's minus 1 is the complex number. Okay, folks, we're going to see how to use this to prove trig identities in the next lesson. You may now have a go at the exercise on the next page.